So my name is Alan Szepieniec. That is a Polish surname, but sadly my father did not speak Polish with me, so I don't know much more than how to order the dry kielbasa. And let's be frank, that's the good kielbasa anyway. This is joint work with a bunch of authors, of which only Ferdinand is a teammate over at Neptune. If you're interested in Neptune, go to neptune.cache. It is the first layer 1 that integrates ZK Starks on layer 1 as part of the consensus logic. I'm moving the mic closer. Okay. Which ZK Starks we are integrating into Neptune is Triton VM. So that's why the second logo is there. And Triton VM is a standalone Stark. In addition to using it in Neptune, you can use it for anything you want. Now, we're big on Starks, and the Tip5 hash function is big on Starks as well, so I'll cover that briefly. The idea is, as I'm sure you are aware, you have an input, a program, and some machine turns that input and that program into an output. And the idea is, this is not a physical machine, this is a virtual machine, and we can make the virtual machine record every intermediate state of that computation. Now we have a trace, and we can feed the input, the program, the output, and the trace into a prover, which then outputs a proof, and that proof can go into a verifier that only needs to look at the input, the program, and the output, and the proof, and the verifier gives you a true or a false with cryptographic certainty. Now that's only half the picture that's motivating the design of Tip5, because we don't just want a hash function for Starks, we want a hash function for recursive Starks. So if we're looking at the green arrows and the green box of the verifier, that's the computation that we want to prove. So that looks more like this. We have a new input, which is the input, the program, the output, and the proof of the previous slide. And we have a new program, which is the verifier of the previous slide. And we have a new output, which is the output of the verifier of the previous slide. The same computation of the verifier is taking place, but now it's taking place inside of the virtual machine. This virtual machine is producing a trace. The prover is producing a new proof for this. And the verifier is taking this proof and verifying that it establishes the correct execution of the verification of another proof. The reason why we want to do this is so that we can split up computations into multiple steps and then prove each step separately and then merge all the proofs, or we want to distribute data and data and other data that authenticates that data, and whenever you transmit that data or combine two pieces of data, you combine their proofs. That's called proof-carrying data. And the whole idea behind Neptune's native support for Starks is to enable that kind of manipulating proof-carrying data. So if we're looking more specifically into the mechanics of Starks, it starts with an algebraic execution trace, and then you do low-degree extension, basically evaluating them as though they were polynomials on a much larger domain. And then you hash, so then you get a table, and then you hash every row of the table to produce a single column. Then you hash the column into a Merkle tree. Then you do some Fiat-Shamir, and then you do a little more arithmetic and lots more hashes, and a little more arithmetic and way more hashes then. So this is a rather complicated picture, but the bulk of the computation here is really hashing. And it's actually more clear if you summarize all the individual steps and then put in bold font those steps that involve hashing. There's a lot of hashing that goes in here. And even though theory predicts that the bottleneck of producing a Stark proof would be that low-degree extension step, because that is asymptotically superlinear, whereas hashing is only linear. In practice, 80% of the time was spent hashing. This was still using the rescue hash function, mind you. So if we want faster Starks, we just switch to Blake 3, right? That's the fastest hash function, isn't it? Well, unfortunately, that's only half the picture, right? Because we want a verifier, and this verifier has to run in the VM. And so the VM has to support hashing, because the verifier needs to do hashing in order to verify the proof. And so we need an arithmetization-friendly hash function. That's great. We have Rescue and Poseidon, don't we? So you can plot them on a graph. On the one axis, you have the arithmetic cost. How much are you paying in terms of proving time in order to prove the correct evaluation of this hash function? And on the other axis, you can have the throughput of your hash function as measured on a CPU. And so Poseidon and Rescue have a very small arithmetic cost, but at the expense of a slow CPU performance. And on the other end of the spectrum, we have Blake 3. We have AES, which is technically a block cipher and not a hash function, but that doesn't matter. We have Keccak, which is not as fast, but it's still pretty fast. But they're all insanely expensive if you want to prove their correct execution. And then somewhere in the middle, we have this weird animal called reinforced concrete. That's also a hash function. It's not as fast, but on the flip side, its arithmetic cost is not as great either. And what I want to convince you of is that Tip5 belongs in this picture on the top left. Low arithmetic cost, not quite as low as Rescue and Poseidon, but its performance is on par with Keccak. In terms of security, statistical cryptanalysis is mostly well understood, especially in relation to traditional hash functions, and Tip5 borrows a lot of design principles from traditional hash functions. So the statistical cryptanalysis part is not the interesting part. The interesting part is the algebraic cryptanalysis. And in order to illustrate why algebraic cryptanalysis is relevant, let's make a slight detour to the land of Gröbner bases. Here is a system of polynomial equations in two variables. How do you solve it? Question for the audience. Any takers? This is only degree 3, really low degree, but we have two variables and two equations. So there are 9 solutions. There are 50 people in the room. No, it's actually quite difficult, but once you know the underlying mechanism by which you could go about finding solutions, you'll see Rescue and Poseidon as prime targets to attack using this family of algorithms. This family of algorithms known as Gröbner basis algorithm. So the way we're going to do this is we're going to transform these two equations into a matrix. This matrix represents that system of polynomial equations because after moving all the terms to the left-hand side of the equations, we have polynomials. We can drop the equals to zeros part, and we assign a monomial to every column of this matrix. So the monomials here are x cubed, x squared y, xy squared, y cubed, x squared, xy, y squared, xy, and 1. So every polynomial that you could write corresponds to a row in this matrix, and every column in this matrix corresponds to a monomial. Now, Gröbner bases are traditionally defined with respect to multivariate polynomials, but this matrix interpretation allows me to convey the intuition much more concisely. because what ends up happening is linear algebra. We want to perform Gaussian elimination on this matrix, except we can't, because this matrix is already in row reduced echelon form. So we can't read out a solution. But what we can do is we can take these equations and multiply them by monomials. We can multiply the top equation by x and y, and we can multiply the bottom equation by x and y. And then we get new rows in the matrix. Unfortunately, we also get new columns. So the matrix grows, but at some point we will get more rows than columns. This is a fact of combinatorics. And once we have more rows than columns, we can run once we have more rows than columns, we can run Gaussian elimination, push it into row-reduced echelon form, and read out a solution. The question is, how big does this matrix have to get before it's successful? And the answer to that question is, it depends. It depends on the degree of regularity, which is a property of the system of equations that you start with. So, back to arithmetization-oriented hash functions. If we're going to use rescue or Poseidon or Tip5 or reinforced concrete, what is the degree of regularity? Very important question. Because if it's arithmetization-oriented and easily provable in the context of a zero-knowledge proof, that means by definition that there is a compact description of the hash function in terms of multivariate polynomials. And so Grosvenor basis algorithms are relevant by definition. In the case of Poseidon, the designers assumed that the degree of regularity behaves like the worst case, like it behaves in the worst case. And this assumption has been falsified. Poseidon 1. This is Poseidon 1. I don't think Poseidon 2 has any different behavior, because it's only the linear layer that's different, if I'm not mistaken. To be clear, this doesn't necessarily give rise to an attack on Poseidon. It just shows that the designers overestimated the security, at least against Grosvenor basis attacks. For rescue, we knew that we shouldn't assume that degree of regularity is what it is in the worst case. So we extrapolated from small instances. But unfortunately, this is a very ad hoc approach to estimate the degree of regularity. We're making the assumption that extrapolating the degree of regularity from small instances is a sound approach. And that assumption is questionable. And with respect to reinforced concrete, I tried to attack it and I can't. There doesn't seem to be a straightforward way to apply Grosvenor basis attacks to hash functions that involve lookup gates. So, to summarize the last 5 minutes, lookup gates are actually kind of strong against Grosvenor basis attacks. So, let's use reinforced concrete, right? Well, unfortunately, there are a couple of design parameters that make reinforced concrete not the ideal hash function. The prime field over which reinforced concrete is defined is not friendly for Starks, and, well, we really want that prime field. Some people call it the Goldilocks field. We call it Oxvoy because we want it because it's very easy to prove the correct decomposition of 64-bit integers into two 32-bit integers. We want the rounds of our hash function to be uniform so that there's a simple system of error constraints that proves the correct execution of the hash function, whereas reinforced concrete has different rounds depending on where you are in the cipher. Reinforced concrete has a state that consists of 3 field elements, and we want 16. That allows us to shrink the number of rounds and still process the same amount of information. So those are the design constraints that went into Tip5. And it's also motivating why we have yet another hash function. So we have 4.5 minutes left. Let's jump through the description of the hash function. But the most important thing was the motivation, which I hope I got across right now already. So it's a sponge construction, which means that the only thing we need is a permutation that's difficult to distinguish from random. And then the capacity part, that's the bottom 6 elements, you never touch. But in order to hash data, you overwrite the top 5 elements. This is a sponge construction in overwrite mode, not in addition mode. So the only thing we need is the permutation. What does that look like? Well, I already said we want uniform rounds. So the fact that this is symmetrical going sideways should not be surprising. Let's look at one round. There are 4 different components. Firstly, there is addition over the finite field. What's being added are uniformly random constants. The MDS matrix is just matrix vector multiplication. This is a special matrix because it's a circulant matrix. This is the TS box. This is just the lowest possible power map that's invertible. And the SS box, that's the special one. That's the S box that uses lookups. So specifically what we do is we take a field element and we split it up into bytes. Remember, this field has almost 2 to the 64 elements. So splitting up into bytes is more or less possible. Then we apply this map. X goes to x plus 1 cubed minus 1 over a different field. This field has 257 elements. And then we combine those bytes again. And so we know that the entire thing has to be a permutation. Addition with known constants is easy to invert. An invertible matrix is easy to invert. The power map was chosen to be invertible. But how on earth can that thing be invertible? How is it a permutation? In order to prove that it's a permutation, look at that inner function. It's defined over the field of 257 elements, and it has 3 fixed points, of which 256 is 1. So we can drop that 1 element from consideration and consider the set of elements from 0 to 255, and it's still a permutation over that set. So it's a permutation of bytes to bytes with fixed points at 0 and 255, meaning that it sends all zeros to all zeros and all ones to all ones. And then there's a little bit of math that allows you to show that the entire thing is a permutation. If x is greater than p, then it has this description, and the all ones get sent to all ones by the S box. And so we don't care because the result is still greater than p or equal to. If x equals p minus 1, that's minus 1 mod p, well, then it has to look like this. And the all ones get sent to the all ones by the inner S box, and the all zeros get sent to the all zeros by the inner S box. So this guy gets sent to p minus 1. And anything smaller, as a consequence, is sent to something smaller as well. So the entire thing is a permutation. The circulant S box, this is, the circulant MDS matrix, this is where a little bit of algorithm design came into play, because the idea is we want to compute this over the integers and then delay the modular reduction. And the way we achieve this is by interpreting the matrix vector product as a product of polynomials. We can do that because it's a circulant matrix. And then we factor the polynomial modulus of this product. And we separate this product over the 2 respective factors. One we compute using Karatsuba, and the other one we compute recursively. Karatsuba and recurse, and so on. That's what gives rise to our MDS matrix multiplication procedure. These are the main highlights of the Tip5 hash functions. Please hit me up if you have any further questions. You can follow me at Szepieniec on Twitter. Thank you.